Fantastic. So our second lecturer is Reza. Reza is currently a lecturer at DMU, the competition, again in the Theatre Institution, but we can like the sound will be good. Reza's going to talk to us about flow of fine and cohesive powders really under controlled air pressure conditions. And I think we should say to you, somebody told me it's New Year Day today in France.
Yeah,
so we should wish you Happy New Year as well.
Thank you very much.
It's appropriate to give your Doctoral Inaugural Lecture on New Year's Day. So Reza, please.
Thank you very much. Thank you. Thanks everyone for coming to this talk. Just a little background about my academic life first. I started my undergraduate in Iran. I did mechanical engineering, and then I moved to the UK to do advanced mechanical engineering for masters, and then I started my PhD under the supervision of Dr. Baserinia. After completion of my PhD, I worked as a research associate for a very short amount of time before joining DMU as a lecturer. And today I'm going to talk about the flow of fine and cohesive powders under controlled air pressure conditions. Just a quick overview. First I'm going to provide an introduction to powders and powder flow. Then I'm going to present you with some powder characterization methods before moving to the experimental studies that I carried out in my PhD, and finally present you some of my future plans for the years coming. So in our everyday life we use a lot of products that are in form of powders or are manufactured from powders. These varies in many different industries. For example, you use coffee, use sugar, salt. These are all in particle form. Also, we use powders to manufacture pharmaceutical tablets or some components that we use in equipment such as car, for example, gears. And in the range of industries that we have, we use several different processes such as the granulation process, milling, roller compaction or direct compression in order to manufacture the powders or the products from the powders. In all of these processes we have the flow of powder, where the powder goes through silos, hoppers, chutes, feeders, whether it's a linear feeder or a rotary feeder. In order to design a final product with given sets of attributes, we would need to understand what the material properties are and how they influence the final properties of our product. We would also need to know how the processing parameters such as the geometry of the container that we are using or the environment that we are manufacturing the component in influences the properties of the materials. And in fact, the processing parameters are influenced by the material properties as well. Just to give you an example, in pharmaceutical industry, 70% of the products are in forms of tablets, where they are manufactured in rotary tablet presses, such as the one that we see in the image. Some of the final properties of the tablets are the mechanical strength, the density of the tablet, or the weight and size uniformity. And if you're unable to control these properties, these can have very serious effects when the patient takes the drug. For example, mechanical strength and density can influence the disintegration rate of the tablet within the body, while the weight and size uniformity affects the drug content of the tablet. So we would need to understand how different parameters influence the final properties of the products that we are designing. We can categorize the parameters influencing powder flow into three main groups: the material properties, including the particle properties and bulk properties of the powder, the processing parameters, and also the environmental parameters. And that's where we design my research objectives in the PhD. So my objective was to understand the influence of material properties and processing parameters on powder flow behavior in pharmaceutical processing operations, and also to develop relationships relationships to describe powder flow in these processes. And to start with, I selected 6 different powders. These are all pharmaceutical excipients, 4 grades of microcrystalline cellulose, pH 101, pH 102, pH 200 and pH 302, calcium phosphate grade ATAP, and mannitol grade perilitol 200 SD. And to obtain an understanding of how these powders behave and to get some understanding about the properties of these powders, we did a range of different experiments. To start with, we measured the particle size distribution of the powders. This gave us the average particle size of the powders that we were using, and also the span of the graph gave us what portion of the powders we were using were fine particles. And based on the data, we could identify the influence of particle size and also the bulk density of the powder in the experiments that we carried out. The next experiment was measuring the bulk density of the powder. So bulk density is just the weight of the powder in a given volume. So the experiment included a cup with a given volume, and we used the powder conditioning device to fill the cup and measure how much the weight of the full cup was in order to identify the bulk density of the powder. The next technique that we used to identify the flow behavior of the powder was the critical orifice diameter. Critical orifice diameter is the minimum diameter required in a container in order for the powder to discharge freely under the gravity. So the experimental setup consisted of a cup where we placed a disc with a given orifice diameter at the bottom of it, filled the cup with the powder conditioning device, and then we released the pin for the shutter to open. If the orifice diameter was large enough, the powder discharged freely. We repeated the experiment and we recorded the minimum diameter required for each of the materials used. And the second experiment we used to characterize powder flowability was the angle of repose experiments. Angle of repose is the angle of a heap of powder on a flat surface. And in the experiment we used 3 bases of 50, 75 and 100 millimeter diameter, and we formed the heap onto the flat surface and we measured the angle that the heap had on the surface. This table summarizes the data that we got from the experiments that I explained. We can see the average particle size of the 6 powders in the second column, and also the bulk density of the powders. Looking at the critical orifice diameter values and the angle of repose, we can characterize the powder flow behavior where in critical orifice diameter, if a powder has a smaller critical orifice diameter, it means that it's a better flowing powder, while for the angle of repose, if a heap with a smaller angle is formed, we have a better flowing powder. And we can have a number of observations based on the data that we have. The first observation is that the powder flow ranking depends on the technique that we are using to characterize the powders, and we can see some variation in the ranking obtained based on the critical orifice diameter data and the angle of repose. We can also see that for one simple technique, even if we change the processing parameters such as the base diameter and the angle of repose experiment, we will see some variation in the ranking that we observe for the powder flow. In many of the powder processing operations, the powders are in contact with air, and air has a large influence on how the powders behave. And in order to quantify the powder-air interactions, we use the powder permeability experiment, where we design the container, fill it with powder, and allow pressurized air to pass through the powder. Then we measure the differential pressure appeared across the powder bed and use Darcy's law in order to calculate the permeability of the powder. And based on the values, we calculated the powders can be ranked where pH 200 has the highest permeability, with pH 302 as the least permeable powder. This suggests that powder-air interactions are more significant for pH 302 compared to pH 200. Just to summarize the key observations that we had, the powder flowability changes by changing the processing parameters. It is specific to the technique used, and it should be characterized using a technique which captures the mechanics of the process under investigation. And after gaining an understanding of how our powders behave, we decided to look at the process we use to manufacture tablets. In the rotary feeding system, in the rotary tablet presses, we use the rotary feeding system. We built a module of it in the university. In the module, we have a powder container which we fill with about 800 grams of powder. The powder is discharged first through the feeder, which you can see in this image. In the feeder, we have four paddles with different cross-section shapes, different exit diameters at the bottom of the feeder, and finally the powder is discharged into a vacuum chamber. This setup allows us to study first the effect of different paddle shapes, the effect of the rotational velocity of the paddles, the effect of exit diameter, and also the effect of differential pressure on the powder flow rate. And we carried out some experiments using this setup. We can see that by increasing the angular velocity of the paddles, we can increase the mass flow rate of the paddles discharged in the system, in the rotary feeding system. We also observed that at a certain angular velocity, the mass flow rate had increased for a poor flowing powder compared to a good flowing powder. We also did some experiments under differential pressure, and we can see that by applying only 100 Pascal of differential pressure across the powder, the mass flow rate discharge can be increased significantly. At this point, we wanted to develop a relation in order to describe, in order to use the parameters involved in order to predict the behavior of the powders. However, the number of parameters involved in the process was very high. So we decided to move one step back and look at a more fundamental problem in powder flow, which is powder arching. So we measure the critical orifice diameter. If the orifice diameter of the container is smaller than the critical orifice diameter, arching appears above the exit, where the powder is blocked in the container and it refuses to flow. One of the methods that they use in the industry is hammering. They use a hammer to smash the side of the container and they will make it flow again. But there is no guarantee to stop it from happening again. Another method to prevent powder arching is to increase the exit diameter. However, in pharmaceutical industry, for instance, we need a fine dosage of the powders, not a really large volume of the powder discharging. So increasing the exit diameter is not really the best option. So we thought about this problem and we suggested to use differential air pressure to make the powder flow. And that's why we designed this system. The system contains of a container for the powder with a disc of a certain exit diameter at the bottom. We have a shutter to stop the powder from flowing initially, and the main setup is basically above the powder, a vacuum chamber. The orifice disc that we used ranges from 1 mm in exit diameter up to 30 mm, and we measured the differential pressure required to break the arch. And looking at the values that we measured, we can see that it's not really a significant pressure required. So a powder that does not flow through an orifice of 30 mm, by applying just about 150 to 200 Pascal, we can make it flow through an orifice of 2 mm. Based on the experimental data and by using the dimensional analysis, we developed a relation to determine the differential pressure required to break the arch as a function of height of the powder and the exit diameter. The next problem to look at was to determine the mass flow rate of the powder through the container. under the influence of differential pressure. Very similar setup to the previous experiment. The container is larger, and we also have a really much larger vacuum chamber at the bottom. First, we increase the differential pressure to a value above the pressure required to initiate the powder flow. Then we measure the mass flow rate required through exit diameters of 5, 7 and 10 millimeters. And we carried out this experiment for the 6 powders that I presented, and we observed that the mass flow rate increased exponentially with the differential pressure. And by using dimensional analysis, I developed a similar model to determine the mass flow rate of the powder as a function of material properties and also the differential pressure that we are applying across the powder bed. So I looked at the powder flow initiation. I looked at powder mass flow rate in a hopper discharge. The next stage was to look at the mass delivered in a linear feeding system. This is the experimental setup that we used. We have a shoe. We filled it with a certain level of powder. The shoe passes over a die and deposits the powder into the die as it crosses over. I have a little animation for you. And as a result of the shoe passing over the die is filled with powder. We measured, for the experiments carried out, we measured the differential pressure above the die and also at the bottom of the punch that we had. In the experiments that were carried out on the gravity field mechanism, when the experiment starts, initially the powder can discharge into the die freely, and we will observe no flow of the powders into the die. And the air that exists inside the die can escape freely through the gap between the tip of the shoe and also the clearance that we have here. As the process continues, the die is becomes fully covered with powder, and it becomes really difficult for air to escape the die. And it can only escape through the clearances in the system or through the powder itself. This will result in an increase in the pressure inside of the die, which would oppose further flow of the powder into the die. So if we can facilitate no flow of the powder, we can have a larger mass delivered into the die compared to when we have a bulk flow of the powder. We measure the differential pressure inside the die, and it proves the theory that as the experiment starts, we see a large increase in the differential pressure inside the die, and as the experiment continues, this pressure dissipates before going back to zero when the experiment is completed. We did the experiment for the 4 grades of microcrystalline cellulose for a range of shoe velocities. We can see that for each experimental setup, the mass delivered into the die decreases significantly by increasing the shoe velocity. However, we can see that at really large heights of the powder inside the shoe, only a specific amount of powder is delivered. When the height of the powder in the shoe is smaller, we have a more facilitated nose flow. That's why we see an increased mass of the powder discharge into the die. Using the model developed by Schneider, we basically fitted the model developed by Schneider to the experimental data, calculated the exponent n, and used the model developed by Hu to basically predict the behavior of the powder, as you can see by the continuous lines on the figure. So we can see that the model can predict the behavior really well. However, the problem with the model is that the coefficient c and the exponent n changes for the different experiments that we carried out. So for every experimental setup, we will need to find a new value of c and n. So it's not really possible to use the model at its current form. So we decided to modify the model by including the effect of powder height in the shoe and also the differential pressure developed into the die during the experiment. And by inclusion of those two parameters, we observe that the model predicts the experimental masses delivered into a die quite well. We still have 3 exponents within this model. However, these become constant values for every material. So once they are calibrated for a material, they can be used for the different values of powder height in the shoe or shoe velocity. After the experiments carried out in gravity field, we did similar experiments in suction field mechanism. In suction field mechanism, as the shoe initially the punch is moved upwards to fill the die completely. As the shoe starts passing over the die, the punch inside the die is lowered and creating a suction effect and sucking the air, the powder into the die. So we carried out the experiments for a range of shoe velocities and suction velocities, and we had some really interesting observations. Based on the gravity field experiments, we observed that by increasing the shoe velocity, we get less and less material inside the die. However, for suction field, we observed that by increasing the suction velocity at a given shoe velocity, we can actually see an increase in the mass delivered. So initially we were expecting to see a smaller mass when the shoe velocity was set to 300 mm per second compared to the shoe velocity of 100 mm per second. But we saw that consistently for all of the 4 materials, we saw an increase in the mass delivered into the die. So this brings the idea of supply and demand within the linear feeding system. So we can say that the shoe is providing the supply and the die is the demand in the process. If the supply is large enough and the demand is large enough, then we will have a larger mass delivered into the die. But if the supply is not large enough, no matter how much the demand is, still we will get a really limited amount of powder inside the die. So this gives the explanation that for any given shoe velocity, there exists an optimal suction velocity at which we get the maximum mass delivered into the die. Looking at the pressure changes within the die during the suction field mechanism, initially the die is completely filled with the punch, so there is no air inside. As the punch starts to move down, air can be sucked into the system from the clearances that we have in the system and also through the powder. Once the suction motion is completed, then the pressure then it becomes really similar to the gravity flow, and the pressure inside the die starts to increase, and again it opposes the further flow of the powder into the die. So we get the suggestion that initially the pressure inside the die should increase as we are sucking, should decrease as we are sucking air into the system, and then it should increase to a maximum value when the suction field period is over and we have the gravity field period. Based on the differential pressure measurements, we observed the same we had the same observations. So initially at the experiments we have a sudden drop in the differential pressure inside the die, followed by an increase in the differential pressure as the suction field period is completed. For really large shoe velocities, because the gravity time is really small, we don't see really a large increase inside in terms of the differential pressure inside the die. Similar to the previous experiments that we carried out, we developed a model to predict the mass of the powder delivered into the die by considering it as the sum of the mass delivered during the suction field period and the mass delivered during the gravity field period. The model is really long, that's why I didn't include it in the slide. Just to summarize, in my PhD studies, I studied the influence of material properties and processing parameters, specifically air pressure conditions, on powder flow behavior, and I developed a number of dimensional models to prescribe and describe the behavior of the powders for the flow initiation experiments, to predict the mass flow rate in bin discharge, and also to determine the mass delivered in linear feeding system under gravity and suction field mechanism. The next step for me is to use numerical simulation like the DEM-CFT studies to basically understand and study the influence of parameters that are not appearing in the model, and also to develop a mechanistic model which should prescribe flow behavior of powders in the systems that I described. Thank you very much for attending the talk. I would like to thank my PhD supervisor for his continuous support throughout my studies, and also our PhD group. Also, I would like to thank my wife, who's here, and my parents for supporting me throughout my studies. Thank you very much.
Very interesting lecture. I've never thought of powders in quite that way before, so that's quite interesting to me. Does anybody have any questions? On the back.
Do you think you'd be able to commercialise this?
The models that we have developed can be used for process optimization. However, for example, the first experimental setup that we have the potential to be used as a powder flow measurement technique. Yeah, so there is a potential.
What about, so, if I was to take 2 paracetamols or some ibuprofen, where the actual pharmaceutical is a substantial component of the tablet, so what does the pharmaceutical do on the bulk flow of the powder? Does that change the powder? Some of these pharmaceuticals are charged and some of them are...
Yeah, they certainly do, because normally the active ingredients within the pharmaceutical formulation are the fine and cohesive particles, and they tend to make the bulk behavior more cohesive. So certainly they would cause more problem in the manufacturing processes.
So if I'm thinking about this right, is what you've got is you've defined a set of parameters that for a given machine you can then define the optimum way in which the tablet is made. So
yes.
This is effectively a kind of blueprint for tablet machines.
Yes, exactly. The models that we have developed at the current stage, they are still empirical models, and there exist some constants within those models which have to be calibrated for each material. So if you have a formulation, then the model have to be calibrated for the model in order to use it. And in the next stage, we are trying to study the influence of other parameters that are not currently included in the model. For example, the friction between the particles, and the container, or the cohesion between the particles, and we want to include those parameters inside the models to come up with a generic and mechanistic model. So no matter what the powder is, we can predict its behavior.
Any other questions? Okay. Can we get a machine photograph with our lecturer? Thank you very much. Nice one, Kelly. And these will go on the website on various websites. No, thank you. Thank you. So thanks again.